Hello everybody, it's been a while. Welcome back to G4 Lab IB Physics, and today we are going to be going over rigid body mechanics and specifically rotational motion. And I've changed the formatting a little, so we're going by the official IB syllabus, and so this will be topic 8.4. Okay, so what is rigid body mechanics? And in the context of IB, we're going to focus on rotational motion for rigid body mechanics. And so think about the forces that act on a car when it turns, or a plane performing a loop-de-loop. These are both great examples of rotational motion in action. And so we will find that oftentimes rotational motion has nice analogs to the translational motion we've been studying so far. And we will mostly be going over like the motion itself, not like how it comes to be, I guess. So centripetal acceleration and that type of stuff will not be in this video. So rotational motion can be modeled with the following four equations, which as you can see here, they're basically the translational motion equations, with the only difference being that we now have like angular terms like theta as an angular displacement. And oh yeah, by the way, the original translational motion formula doesn't have this theta initial, but if you subtract both sides, this from both sides, you get theta final minus theta initial, delta theta, same thing, right? Yeah, and then you have omega, which is angular velocity, and then alpha, which is angular acceleration. And so, yeah, aside from that, these formulas are pretty much the same. It's just a matter of the, I guess, metric for distance. Yeah, no, we don't account for air resistance. Okay, and then so you might have heard of this concept before, and like for instance, you might have heard that tugboats have a lot of torque, despite not being very quick, right? And so that's because torque is much like a force applied to rotate something about an axis. And it's defined as torque is equal to F_r sine theta. If you're really interested, the exact definition of torque should be force cross radius, but in IB we use F_r sine theta. And so here the angle theta is defined so that 90 degrees is like perfectly tangential with the circle the object is moving in. And so like kind of like visualizing this, I guess, remember tugboats need to pull heavy objects, and so they do so by displacing massive amounts of water at once with their propeller. And so to displace such a massive amount of water, we need a very like strong rotational power, and so it requires a very high torque. So this will make more sense as we move on to moment of inertia. So torque has another definition, and before we talk about the definition, we need to intro the concept called moment of inertia. So moment of inertia, as its name suggests, behaves kind of like inertia or mass, but for rotation specifically. And so for a point mass, it's defined as like a moment of inertia is equal to mr squared, and so the unit, as you can guess, is going to be kilograms meters squared. And so what we'll see as well is that different of these like figures are going to have different moments of inertia, and here are some examples. And so for now, we won't worry about how these formula came to be. If you're interested, I believe you can derive them with vector calculus, if I'm not mistaken. And typically for problems, you'll either be given the formula for moment of inertia, or you'll just be given the moment of inertia itself for the figure. So, and then an interesting phenomena we can actually see here is that for like certain objects, like for example a hoop versus a cylinder of the same mass and radius, the hoop is actually going to have a larger moment of inertia. And while we don't have the calculus background to understand why exactly yet, in essence it's because most of the mass is distributed further up, so it's going to have a more rotational mass, I guess you can think of it like that. And so what is torque now that we've covered moment of inertia? What is torque really? And so we can take a look at the other formula for torque. And so we have here torque is equal to moment of inertia times alpha, or angular acceleration. And oh, by the way, the unit for torque is Newton meters. And so if you think about it, this is pretty much Newton's second law, but for rotational motion. And so I'm not going to go over the unit simplification here, but you'll see that it becomes the same as the other one. And just like from here on out, we're just going to basically just be looking at parallels with Newton's laws and translational motion. Okay, so problem number 1, system where a metal rod is attached to some other metal to rotate about a point. It's attached by some other metal to rotate about a point. And so if the moment of inertia of the rod is 3 kilogram meters squared, the rod is 5 meters away from the point, so the radius is 5 meters, and the angular acceleration is 5 radians per second squared, assuming the rod is perfectly tangential to the circle and it would move around. So that just means theta is 90, so we can just ignore that because sine of 90 is 1. So we need to find the force that gets applied to the rod given this information. Okay. So this is just a matter, if you remember, torque had two formulas, and moment of inertia times alpha and force times radius, right? And so because we're ignoring the sine theta, it's just one. So this is just a matter of setting the two formulas equal to each other. So we have 3 times 5, because moment of inertia is 3, angular acceleration is 5, is equal to 5 times the force, because the radius is 5. And so we can just divide both sides by 5. We get the force is 3 newtons. So that is what you'd have to, that's the force you'd have to apply to get the metal rod to just like spin like that, to accelerate at that angular acceleration. Okay. So moving on, now we're going to touch upon angular momentum, and this is basically like regular momentum in translational motion. And it's important to note that just like in translational motion, angular momentum of a closed system is conserved, and it only changes if it's acted upon by a torque. So, and we're going to see that just now. And by the way, if I'm going too fast, you can always pause the video and like take notes on the slides. And the unit is kilograms meters squared per second for angular momentum. Okay, so now we have angular impulse, and so this is much like regular impulse once again in translational motion. So we have the delta angular momentum is going to be equal to delta I omega. So and the unit's going to be the same as angular momentum. And so much like how, so from here we can see that if we have like a change in angular velocity, we will have a change in angular momentum. And so much like how angular or impulse can also be defined in terms of force and time in translational motion, we're going to find a similar definition for angular momentum here. And so we find that the change in angular momentum is also going to be equal to the torque times the time that the torque is applied for. So it's like a perfect parallel actually, because in regular impulse can be defined as force times the time it's applied for. So now we got a second problem. So a disc of metal with radius 2 meters and moment of inertia 20 kilogram meters squared, spinning at 3 radians per second. What happens to the A, angular velocity of the disc, if 2 kilograms of a 2 kilogram box of metal is put on top of it at the edge, assume the box is a point mass. And then B, the angular momentum, if the average torque of 3 newtons meters is applied for 5 seconds. So for problems like this that are a little more convoluted, I guess, we should probably, like, it's a good practice to visualize the problem and what's going on at first before actually doing any math. And so remember that angular momentum is conserved for this one, right? So we can solve this problem by figuring out the initial angular momentum of the disk, because remember it was rotating before, and then dividing that by the new moment of inertia of the system, because remember once you add the box onto the disk, the box is also rotating with assume the box is rotating with the disk. I probably should have included that in the problem. The whole system has a new moment of inertia. So, but because the angular momentum stays conserved, we're going to have a new angular velocity as well to compensate for the new moment of inertia. So the initial angular momentum turns out to be 60, and then so now we have our new moment of inertia for our system, and we have the angular velocity we're solving for. So this turns out to be that should be 28. Sorry, yeah, this is actually incorrect. So yeah, so we have 60 divided by 28, not 24. So yeah, 60 divided by 28, not 24, and so the answer should actually be 2.14. Yeah, not 2.5, 2.14. Okay, and let's move on. So, and then part B, that was a while ago we mentioned this, so let's go look at it again. The angular momentum of if an average torque of 3 meters is applied for 5 seconds. So that means it's just an application of angular impulse, and so all we need to do is apply the formula to see how much the angular momentum changed. And so we do that, we get 15 kilogram meters squared per second. So in other words, the angular momentum changed by a factor of 25%. Wow, okay, cool. Okay, so now we have rotational kinetic energy, and so this is quite similar to translational kinetic energy. And so we have it's equal to 1/2 moment of inertia times omega squared, and so we get the second formula, angular momentum, which is usually denoted as L. Here it says capital L. If you see L, it means angular momentum. Angular momentum squared over 2 moment of inertia, and I'm not going to go over how to get this formula, but you'll see that it's just a rearrangement of the first with different variables. Okay, so now let's go over a phenomena, which is rolling without slipping. And so now that we've gone over both types of kinetic energy, we can examine the situation. A rolling object has both kinetic and rotational energy, and rotational kinetic energy. And so for rolling without slipping specifically, we require that these are the conditions. We require that the instantaneous velocity of the point of the object, assuming it's circular, should be, touching the ground is 0. The translational velocity v is the product of the radius and the angular velocity, or in other words, v is equal to r omega, and that there's sufficient static friction, which static because the point touching the ground has an instantaneous velocity of 0, for no slipping. And in this case, the total energy of the rolling object is going to be the sum of the translational and kinetic energy and rotational kinetic energy. That's written wrong. So oftentimes its energy can be expressed in terms of solely m and v. Though for this problem over here that we're about to do, we actually will not have to do that. So a cylinder of radius 2 meters and mass 10 kilograms at rest rolls down a hill. It ends up at a translational velocity of 10 meters per second at the bottom. So from how high up the hill did it start rolling up? And so here we have some moment of inertia formulas. And so we're going to be using the symmetry axis formula, so 1/2 mr squared from our moment of inertia. And so once again, let's just think about what's happening before we do any math. And so this question might look strange at first, but if we examine it more closely with energy laws, we'll see that the solution is not complicated. So yeah, this cylinder starts from rest and it ends with a certain amount of kinetic energy, meaning it gains a certain amount of kinetic energy, so it has to lose that same amount of potential energy because the energy is conserved. And so if we find the kinetic energy and then we divide that by mass and gravity, because remember potential energy is mgh on planet Earth, where g is 9.81, we can find the height it started at. And so another thing we need to figure out is the angular velocity, but remember the condition for rolling without slipping, v is equal to r omega. So, and we know v and we know r, v is 10, r is 2, so then we can rearrange, we get omega is 5 radians per second. Okay, and then now we can plug in all our information into the formulas to determine the total kinetic energy after rolling down the hill. So, and here we have, so remember we said that the kinetic energy for rolling without slipping is the rotational kinetic energy plus the translational kinetic energy, or in other words, and in our case, I did not write that, actually I skipped a step, but the moment of inertia is 1/2 mr squared for the cylinder, and so as you can see, we plugged in all our variables here. Omega is 5, m is 10, r is 2, whatnot, final translational velocity is 10, and we get that the final kinetic energy is 750 joules. Okay, so we have that. So now this is the kinetic. This is equivalent to the kinetic energy or the potential energy the cylinder lost. So we can set this equal to mgh. We know m, we know g. M is 10, g is 9.81, and then we just need to solve for h. So we can rearrange. H is equal to 750 divided by, that would be 98.1, and that gives us 7.65 meters. So that's how high our hill was. That's how high the cylinder started. Okay. Yeah, so just to review, today we learned that rotational mechanics is much like what we saw previously in regular translational motion, with the main difference being that the moment of inertia replaces mass and radians replaces meters for distance, right? And so we also learned about rolling without slipping and the conditions for this phenomena to happen. Okay. Yeah, that's it. Thank you so much for watching, and be sure to check out our IB Comp Sci and IB video bio videos as well. Thank you.